Hello and welcome to the Maths 2 component of the online BSc program on data science. Today's video is on determinants. This is the second part of the videos on determinants. So let's recall first what we did in part 1. So recall from part 1 that we defined the determinant of a 1 by 1 matrix. So if A is singleton A, then determinant of A is just that number A. If A is the 2 by 2 matrix A, B, C, D, then determinant of A is AD minus BC. You multiply the diagonal terms and subtract out the off diagonal terms. And if you have a 3 by 3 matrix, then we define the determinant by what we called expanding with respect to the first row. So what that meant was you take the 1 entry of the first row, the first entry of the first row, and then disregard everything in the first row and the first column. You get a 2 by 2 matrix remaining. Take its determinant and multiply that with A11. That is the first term. For the second term, you look at A12 and do the same process. Disregard everything in the first row and the second column. Multiply the determinant of the resulting 2 by 2 matrix with A12. And for the third term, you look at A13. Disregard everything in the first row and the third column, take the determinant of the resulting 2 by 2 matrix and multiply it with A13, and then you alternately add these, meaning take the first expression minus the second expression plus the third expression. So that was the determinant of A. So the determinant of the 3 by 3 matrix was defined in terms of determinants for 2 by 2 matrices, and then we can expand this out. We can work out explicitly what the expression is, and you get some rather long and nasty 6 term expression. Okay. So let us do an example just to refresh ourselves, maybe a 3 by 3 example. So here is a 3 by 3 matrix 2, 4, 3, 0, 8, 7, 0, 0, 9. So maybe I should mention that such a matrix is called an upper triangular matrix because it has zeros below the diagonal. Okay, so let us compute its determinant. So determinant of A is 2 times the matrix 8, 7, 0, 9, which is what is remaining if you disregard everything in the first row and column, minus 4 times determinant of 0, 7, 0, 9, plus 3 times determinant of 0, 8, 0, 0. Okay. And then if we work out what these are using the determinants of 2 by 2 matrices, we will get 2 times 8 times 9 minus 7 times 0, which is 72 minus 0, minus 4 times 0 minus 0, plus 3 times 0 minus 0. So this is just 2 times 72 minus 4 times 0 plus 3 times 0, which is just 2 times 72, which is 144. And I will ask you to notice something important, which is that this is 2 times 8 times 9, which is exactly what we have on the diagonal. So these are the diagonal entries over here, and that is what we got. So the determinant of this matrix A is the product of the diagonal entries. So I hope you followed both the computation and the fact that it is the product of the diagonal entries. So this is not some fact specific to this example. This is a general fact for what we call any upper triangular matrix or any lower triangular matrix. So for such matrices, the determinant is the product of the diagonal elements. So I will just quickly recall what is an upper triangular matrix as I said at the beginning. So an upper triangular matrix means if you, so this is a general matrix of size n by n. So this is called upper triangular if you look at the diagonal and everything below the diagonal is 0. So all these entries are zeros. Okay, so we are going to write this as Aij is 0 if I is greater than j. Right. So if the matrix satisfies this property, it is an upper triangular matrix, and this is how it looks like. Similarly, so this is upper triangular. So similarly, we have lower triangular. So lower triangular matrix. So, this is again n by n, that is if aij is 0, if now this time I is strictly less than j. Okay. So, how does that look like? Oops, not a table but a matrix. So, this part must be 0, okay, and these elements can be anything, that any numbers. Okay. So, for such matrices the determinant is the product of the diagonal elements. Yeah. So, of course, we know this only for 3 by 3, and I will suggest that you check this for 3 by 3 and 2 by 2 matrices. Okay. So, let us move on to a special kind of matrix, namely if you have a matrix then its transpose. So, let us define the transpose and compute its determinant. So, in general if you have an m by n matrix, the transpose of this matrix is a new matrix of size n by m. So, it has n rows and m columns. So, remember the first one had m rows and n columns, A had m rows and n columns. So, A transpose has n rows and m columns, and its ijth entry is AJI. Okay. So, the ijth entry of A transpose is whatever was the jith entry of A. Okay. So, just so this is the notation, it is called A superscript T. So, T is for transpose, and its definition as we noted is A transpose ij is AJI. So, just for example, if A is a 3 by 3 matrix, then A transpose is again 3 by 3. So, square matrices, the transpose has the same size, it is also a square matrix of the same size. And what happens to the entries? So, if A is like this A11, A12, A13 and so on, then A transpose is A11, A21, A31, A12, A22, A32, A13, A23, A33. So, okay. So, what happened here? These two entries got interchanged, these two entries got interchanged, these two entries got interchanged. So, the diagonal remains the same. Okay. So, it reflects about the diagonal if you prefer a more geometric way of thinking about it. Okay. So, that is what happens in the transpose. Okay. So, what do we want to do now? We want to compute what is the determinant of the transpose. So, let us work this out. So, determinant of A transpose. So, we have a clear formula for the determinant. So, let us use that. So, we look at the 1 term of A transpose and we multiply by the determinant of what is left when we drop the first row and column, and minus the 1 term of the transpose times determinant of whatever is left when we drop the first row and second column of A transpose, and plus the 1 term of A transpose times determinant of whatever is left when you drop the first row and the third column of A transpose. Okay. So, if we do that, then this is exactly the expression we get, and now we can work out explicitly what happens, and you will see that the final expression you get is just some is just the same as the expression for determinant of A, except that the terms have changed places, but it is the same expression. So, this is just determinant of A. So, what is the upshot? If you take the transpose of a square matrix, then its determinant remains unchanged. Okay, and we have in fact proved this in the 3 by 3 case. I will request that you do it for the 2 by 2 as well. 1 by 1 there is of course nothing to do. Okay. So, now let us move on to minors and cofactors. So, this is a very important idea, and this is what is going to help us to generalize the determinant to the n by n situation, meaning where the size of the square matrix is n by n. Okay. So, now suppose A is an n by n square matrix where n is at most 4. Okay. We will do it in this particular case. So, n is, so either it is a 2 by 2 matrix or a 3 by 3 matrix or a 4 by 4 matrix. Okay. Then the minor of the entry in the ith row and jth column is the determinant of the sub matrix formed by deleting the ith row and the jth column. Okay. So, we have been doing this process in computing the determinant, right. So, to compute the determinant of the 3 by 3 matrix, for the first expression in the determinant, we take A11 times determinant of the 2 by 2 matrix, which is obtained by deleting the first row and first column. Okay. So, now we are talking about just that part, okay, just that operation. So, you look at the ith row and the jth column and you delete those, and then you get a matrix of size n minus 1 by n minus 1, okay, and then you look at its determinant. Okay. So, now this makes sense because we have defined determinants for 2 by 2, 1 by 1, 2 by 2 and 3 by 3 matrices. Okay. So, if you take a matrix of size 4 by 4 and you delete the ith row and the jth column, you will get a matrix of size 3 by 3, and then you take its determinant. Okay. So, this is called the ijth minor and it is denoted by Mij. So, here is an example. I said a lot of words. So, here is an explicit example. So, if A is a 3 by 3 matrix as written here, A11, A12, A13, A21, A22, A23 and A31, A32, A33, then the 1 1 minor, the 1 1th minor is nothing but determinant of A22, A23, A32, A33. Okay. So, this is what you obtain by dropping the first row and first column. This is exactly the kind of operation we have been using in computing determinants by expansion along the first row. Okay. And let us go ahead and first define what is the ijth cofactor. So, the ijth cofactor is where you take the ijth minor and multiply it by a minus 1 to the power I plus j. Okay. Why is this sign coming? So, as we saw in the expression for the determinant, there was an alternating sign, right. The first term was with a plus, then you subtracted the second term, then you added the third term. Yeah. So, it was alternating. So, somehow this minus 1 to the I plus j is supposed to take care of that sign. Okay. That is why we have the sign over here. Okay. So, it is the same number, but it could be with a minus sign depending on what is I and what is j. Okay. So, for example, C11 is just minus 1 to the power 1 plus 1, which is minus 1 to the power 2. So, minus 1 squared is 1 times M11. So, it is minus 1 squared times M11, which is just M11. Okay. So, as a similar in similar light, if we have C23, then this is minus 1 to the 2 plus 3 times M23, but now 2 plus 3 is 5, which is odd. So, minus 1 to the power 5 is minus 1. So, this is minus M23. Okay. So, it depends on what is I and j, accordingly we will pick up a minus sign. So, I hope it is clear what the what cofactors and minors are. So, let us now try to rewrite the determinant in terms of minors and cofactors. Okay. So, for a 3 by 3 matrix, so we have determinant of A is, this is expansion along the first row, this is the definition, A11 times determinant of the matrix obtained by deleting the first row and column, aha, and then you take its determinant. But that is exactly what we called the minor, right, and then minus A12 times determinant of A21, A23, A31, A33. So, you deleted the first row and second column and then took the determinant, but that is exactly what we call the 1 2th minor, and then similarly for the third term. So, we can rewrite it now in terms of our minors as A11 times M11 minus A12 times M12 plus A13 times M13. Okay. So, we are just rewriting these determinants as minors. This was the definition, if you remember from the previous slide. Okay. And then if I want to take care of this sign, right, there is a minus sign here and I want to write everything as a plus. So, then I can rewrite this as A11 times the 1 1th cofactor plus A12 times the 1 2th cofactor plus A13 times the 1 3th cofactor. Okay. So, that is why we introduce cofactors. If we want to not remember the signs, then we will take care of those signs using the cofactors. Okay. So, this is the expression for the determinant of a 3 by 3 matrix in terms of the minors. And remember, the minors meant or the cofactors, the minors meant that you compute determinants of 2 by 2 matrices. Okay. So, now we can go beyond. So, maybe first we should remark that this formula works even for a 2 by 2 matrix. So, if you take a 2 by 2 matrix, so say A, B, C, D, then the determinant is A D minus B C. So, we can rewrite that as A times M11 minus B times M12, right. So, C is exactly M12 and D is exactly M11, or if you want a plus sign, then we can write it as A times C11 plus B times C12. Okay. So, check this. So, now we can use this to generalize beyond n is 3. So, let us generalize this to A 4 by 4. So, suppose you have a 4 by 4 matrix now, then how do we define the determinant? So, the determinant is, this is expansion along the first row. So, the determinant is, you take minus 1 to the power 1 plus j, because we have the first row here, A 1 j times M 1 j. Yeah, this is exactly the expression that we have up here, right. This is exactly this expression here, yeah, except that this is for 3 by 3. I am writing this same expression for 4 by 4. And if you want to take care of the signs, not bother about the signs, then you can write it just as a sum of A 1 j times the corresponding cofactor for the 1 jth term. Okay. So, let us maybe write this expression down explicitly. So, what does this mean? This means that the determinant of, so for a 4 by 4 matrix, so A 11 times determinant of whatever you get after dropping the first row and the first column. So, A22, sorry, yeah, A22, A23, A24, A32, A33, A34, and then A42, A43, A44, right. That is your first expression, the first term in this sum, then minus A12, and I will maybe write one more term, sorry, there should be a determinant here, determinant of. So, now we drop the first row and the second column. So, now we get A21, A23, A24, A31, A33, A34, and then A41, A43, A44. Okay, that is the second term in this expression, and note we have a minus sign here, and then plus A13, and I hope now you can write down these two determinants. So, check out what this is, and then minus A14 times determinant of whatever we get here. Yeah, okay. So, check these two terms, see if you can write down these two terms, that will mean you have understood what is going on. So, what is the point here? The point is, we could write the determinant of A, we defined it, this is a 4 by 4 matrix, in terms of determinants for 3 by 3 matrices, right. So, in other words, if I know how to define the determinant for a matrix of smaller size, then I can sort of use this process inductively and generalize, okay, and that is exactly what we do. So, here is the inductive definition of the determinant. So, suppose you have a matrix of size n by n, and we know how to define determinants for size n minus 1. So, n minus 1 by n minus 1 matrices, we know how to define the determinant. Okay. So, then we will define minors and cofactors as before. So, what does that mean? The ijth minor is the determinant of the submatrix found by deleting the ith row and the jth column, right. So, we delete the ith row and the jth column, we get a matrix of size n minus 1 by n minus 1, and we look at its determinant, that is called the ijth minor. Okay. This makes sense, because we have assumed that we know how to define matrices, sorry, determinants for n minus 1 by n minus 1 matrices. Okay. And then if you want to again we are going to do something similar to what we did earlier. So, if you do not want to bother about signs going ahead, you define the ijth cofactor as minus 1 to the power I plus j times the ijth minor, and then we define the determinant of A as the, again this is by expansion along the first row, as minus 1 to the power 1 plus j. Now this sum runs from 1 through n, because remember there are n entries in the first row. So minus 1 to the power 1 plus j a1j times m1j, and again if you don't want to bother about signs and you just want a simple sum, then you absorb that sign into the minor and you can write it in terms of cofactors. So summation a1j c1j. Okay, so maybe let us write down this expression. Let me write down the first term. So now suppose let us say I have a n by n matrix. So this determinant of A is a11 times determinant of whatever you get by deleting the first row and the first column. So you will get a22, a23, and it will run all the way till a2n. Okay, and then below you will have a32, a33, and all the way up to a3n, and if you complete this you get go all the way up to ann. Okay, and then the second term is going to be minus a12 times determinant of a1 sorry, not a1, a21, a23, and then you keep going up till a2n, and then you have a31, a33 going up till a3n, and you keep doing this. Here you will get the first column, here you will get the third column, meaning all the entries remaining in the third column, and here you will get the nth column, and then you keep going, right. You have a12, then you have a13 times determinant. See if you can write down this term, and then minus a14 times some determinant, and note what is happening. These determinants are of smaller size. Okay. So now if I want to do this for a 5 by 5 matrix, I will need to compute the determinant of a 4 by 4 matrix, but I know how to do that. Okay, which means I now know how to compute the determinant of a 5 by 5 matrix. But then I can use the same inductive definition and go for a 6 by 6 matrix, and then using 6 by 6 to 7 by 7, and then so on to 8 by 8, and then using that to 9 by 9, and you can see that inductively for any number I can do this process. Okay, so that's the idea of the determinant. So this is a very complicated looking definition, and yeah, it's kind of a quirk that it's indeed very useful. In fact, I can't emphasize how useful. You will see it later when we solve equations, and later on when we do vector calculus. Okay, so maybe as an example, let us compute the determinant of the identity matrix of size n. Okay. So remember, the identity matrix had 1 on the diagonal, so and everything else is 0. Okay, so this is shorthand to say that everything else is 0. Okay, so let us use the definition. So by definition, this is 1 times determinant of whatever the 1/1th minor. Okay, 1 times the 1/1th minor. So determinant of, you drop the first row and first column, so you get 1s on the diagonal and 0s on the off diagonal. So this is again a identity matrix of size n minus 1 by n minus 1, and then minus 0 times the 1/2th minor, but I don't really care about computing it, because it's 0 times something, it's going to be 0 anyway, plus 0 times the 1/3th minor, and so on. So all these terms are going to be 0, because in the rest of the first row all the terms you have are 0. So what do you get? You are left only with 1 times determinant of the identity matrix of smaller size. Okay. So determinant of in is determinant of in minus 1. That is what we obtained by this process. Okay. And then I can keep doing this, right. So this is determinant of in minus 2 and so on. So the correct way of doing this is what is called induction, and doing this we will reach all the way down till maybe I3, which in or I2, whichever you prefer, and both of these we computed in the previous video to be 1. So, let us recall what we have done in this video. We started by defining recalling the definition of the determinant for the 1 by 1, 2 by 2 and 3 by 3 cases, and we saw that for the 4 by 4 matrix we can define the determinant by using the 3 by 3 definition, right, because we can do that for the 3 by 3 using the 2 by 2 and for the 2 by 2 using the 1 by 1. So, it follows that for the 4 by 4 we can use the 3 by 3 definition, and then we generalize this to the n by n matrix. So, we said that if we can define the determinant for an n minus 1 by n minus 1 matrix, then we can define it for an n by n matrix. So, this is called the inductive definition of the determinant. And finally, we have computed, we did one example, which was we computed that the determinant of the identity matrix of any size 3 by 3, 4 by 4, 5 by 5, 10 by 10, any n by n is 1. Thank you.